welcome to this introduction to Theory of Relativity. We'll first introduce ourselves, then we introduce very briefly what we are going to talk about, and then we kind of dive into physics.
Do you hear in the back row, because that's kind of would prefer to talk without the microphone.
One person hears, how about the others? Okay, great. So, first, let's start with introductions.
So,
My name is Sauli Samila. I'm here because I watched a YouTube video. Yeah. So I do have a master's degree in technical physics. I have studied this topic on my own since I was a teenager. So I do have the physics background, but I watched a very good YouTube video which made things click. So that I kind of, instead of thinking this is an abstract thing I don't understand, I started, hey, this is very cool, mind-boggling thing that I actually do a bit understand. Then we have...
my name is Mikko Parviainen. I have also a master's degree, but I haven't studied space technology, which study in itself didn't have much to do with theory of relativity or anything. It's more like building satellites and rockets and that kind of stuff.
Actually, you're wrong. The timing of the satellite communication is related.
Yeah, there is some, but there's the we will come to that. But the studies at the University of Technology master's program didn't have much to do with it. Then after doing my master's, or I did my master's thesis while researching active gases in the now University of Aalto. So I kind of went into, I was working with this flying satellite, which was cosmic background microwave satellite, which did have lots to do with special relativity, and I started to read about it in that. And after I quit that job after graduating with masters, and then I did I've read much about special relativity, and I've been interested in space for a long time, so that's kind of why I was in the space technology.
Okay, so what we are going to talk today is, first we start kind of history, what led to the theory of relativity. Then we have kind of two sections, special relativity, which means what happens when something something travels near speed of light. So that's, things start getting interesting when that happens. Then we talk about general relativity, which is applying this kind of things into accelerated objects, including gravity, and so forth. That's why we're going to talk about, let's say, black holes and such. Then we will conclude this to how to apply this to your science fiction settings, or if some other setting has near speed of light things or heavy gravities. Because this is a role-playing convention that ties this into hopefully some maybe a bit realistic settings. Okay, so theory of relativity was made by Albert Einstein, but a lot of things happened before he did his part in this. First of all, very important concept of the whole relativity and frames of reference, which we will introduce with more detail later, was established already by Galileo Galilei. Then some, I think, decades before Einstein, Michelson and Morley did an experiment where they tried to, or where they measured the speed of light. And this was kind of groundbreaking things because it made no sense what they realized.
The speed of light had been measured before. People knew, looking at Jupiter's moons, that the speed of light was constant, but...
Yeah, so they tried to measure it in multiple ways. You know that Earth rotates over 1,000 kilometers per hour. Earth circulates Sun, I can't remember which speed. So if you measure now speed of light shooting it to that direction, 12 hours later, we are traveling opposite direction. So if there would be an absolute frame of reference, we would get kind of 1,000 kilometers more and 1,000 kilometers less for the speed of light. But they didn't. They tried it different times of year, different times of day, different directions, but it was constant. And that was kind of groundbreaking, because at that point people thought that there would be ether, which is kind of static things and things move in the ether, or relative to the ether. Okay, then I think it was a decade or two before Einstein, Antoine Lorentz and George Fitzgerald made some adjustments to theory of magnetism and electricity so that they could kind of have this constant light speed for physics, but they really didn't know what they were doing. They kind of hit right things, but were perplexed still what they were doing. And then Jules-Henri Poincaré suggested that maybe some clocks are slower and some are faster. And this now is what the theory of relativity is not fully about, but it's hitting the mark. Do you want to take Einstein?
Yeah, but then there was this guy Einstein, which everybody remembers about theory of relativity. But as we saw, he's kind of the one guy who wrote it. Somebody else, if he hadn't done it, somebody else probably would have done it. But he was born in Germany at the end of the 19th century, got married twice with 3 children, and couldn't get, well, his family life is not part of this presentation, so you can look it up if you want. But initially he wasn't a bad student. Like, there are rumors that he was a bad student and couldn't get degrees and all that stuff. No, he was a good student, but he couldn't get an academic job. Like nowadays, getting an academic job is not certain anyway. So he got a job at Swiss Patent Office, which was great because he had lots of free time, so he could do lots of stuff. And he did a lot of stuff. Like, he didn't only invented theory of relativity. He did in 1905. He had 5 academic papers which started quantum mechanics, defined the special theory of relativity, defined mass and energy equivalence, which is also part of this, and contributed to the atomic theory. So he kind of was in at least 3 areas. He was a big he did good research there. He moved in, then he got an academic job, and then he could write the theory of general relativity more properly. And he got a Nobel Prize, but it was the discovery of the photoelectric effect, which is basically the discovery that kind of started the quantum mechanics. Of course, there was lots of other things, but he kind of contributed to the start of that in addition to the theory of relativity. And quantum mechanics is kind of the other part. I think even nowadays one of the great unknowns in the physics is how to combine quantum mechanics and quantum physics and theory of relativity, because both work, but they are very different. And he moved to in '33 to USA in order to avoid Nazi persecution, which was kind of understandable at the time. And then he worked as a researcher there for the rest of his life, basically.
Okay, the stop sign is here because this is important, which I'm going to say now, and a lot of the rest of the presentation will build on this. So we will spend on this frames of reference some time, so that we hopefully get everyone to understand what we mean with frames of reference. Now, as said, there is no kind of absolute thing that says this is if this is your kind of grid, and when you move against the grid or anything like that. There is just frames of reference. This room is good frame of reference because everyone is from this viewpoint, everyone is sitting still, we are at rest, there is no difficult. But as mentioned, Earth is rotating, we are actually traveling in space with quite a speed compared to Sun or compared to Moon or compared to galactic center. So the point is that all these frames of reference are equal. So now we could pick any one of us as a frame of reference, Para here, and please stay. So if I walk here now, I'm moving in relation to Para. But we can pick myself as a frame of reference and you are moving compared to me. And these are equivalent. It's much easier to have Para standing here as a frame of reference, but that's not a special case. Anyone can be, anything can be the frame of reference where we say this is the frame of reference. Now the whole Earth is rotating under me. I am the center of the universe. And this becomes very important when we start looking at the laws of physics, which say that they are the same in all frames of reference moving at constant speed. So when I start walking, if I walk at constant speed, I'm fine point of reference. So if we go to the bit more examples, these people in the train, we don't know if they are moving. If you can't see outside, if you are in the train, can't hear the clunk, 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 you don't know if it's moving or not. That means if they drop a ball in the train, it drops straight down from their viewpoint. Even if it's going 200 kilometers per hour, it drops straight down. If Pare would be looking from outside, Pare would see the train, which is the ball, the train, which are moving. Pare would see that the ball kind of drops with angle, but they don't see it. And this is what Galileo basically said: if you have something moving at constant speed, you're in it, you can't make a test which says you're moving or not. You have to look at the outside reference to know that you're moving towards some reference point, where that is then the frame of reference. And otherwise, bouncing a basketball in a train moving 500 kilometers an hour, airplane 800 kilometers per hour, fine, you don't need to think that if you drop it, it goes to the back of plane with large speed. Now, I would hope you ask now questions about this, or is this somewhat clear? What is a frame of reference?
And remember that now we are talking about constant speed. So anything moves, it just moves
At
that speed as long as it moves, as long as it's for the whole eternity, basically, without turning, without doing anything.
And this is usually a bit difficult for us to understand because of air in planet Earth, which usually makes everything eventually stop from Earth reference point or some fixed reference point. But especially in space, that's no longer a case.
Yeah, now of course on Earth, because Earth is rounded and it's rotating, so you can easily, basically you can see in a train some things because there are accelerations anyway. But you can say that there are many cases where there are no accelerations, then it's goes.
Yeah.
Okay.
Yes. So now we go to the special relativity. We'll spend some time on here, so you don't need to understand everything based on this slide. But what Einstein basically took two things as the basis or the principles, how he then derived everything else. First one is non-accelerating. So constant speed frames of reference are equal. If I'm there walking. My reference or Pare's reference point of view,
Yeah.
yes, they are equal. The same laws of physics have to apply. Then the other one, which comes from the Michelson-Morley experiment, that speed of light in vacuum is same for everyone, which starts now twisting everything. So if Pare is walking towards me, he sees a light. Okay, let's take it. Flashlight. The light from the flashlight, walk here, is coming with a light speed from him, but he's moving towards me, so I actually see the light coming at light speed towards me, even though you would assume that it comes with Pare's speed plus light speed. So that makes things really interesting when we start reaching speeds that are close to light speed, where you can kind of start seeing differences. In everyday life, that doesn't matter unless you are doing things like GPS satellites or something. Then you start finding these things. So what Einstein came up based on this is that length, speed, mass, and time are relative. They depend on the frame of reference. They depend on the speed. He also came up with relation of mass and energy. This is the EMC, E equal to mc squared. We come back to that later to describe what it actually means. And he came up with speed of causality. That if you go above the speed of light, you kind of run into troubles. Again, we will explain that a bit more later. And then relativity of simultaneity, which means that if I say something happens at the same time as another thing, moving Pare or the rocket, the person doesn't see it the same way. They see things happening at different times compared to what I see. This is a quote from an audiobook, actual book translated into audiobook, which I can't remember, so there is no quote where I got this one. Theory of Relativity is, according to this quote, most tested theory ever. Newton's theories are much more well known, much more understandable, but everyone relies on them. We don't test them anymore. This is quite groundbreaking stuff, and last 100 years we have, as a humanity, done a lot of tests on this. A lot of large experiments on gravitational waves and, okay, not a special relative. Gravitational waves are actually later on general relativity. But a lot of tests have come on the theory of relativity, not just special relativity. Okay. So, now we come to the one of the ways describing why this happens. So, if I sit in a train and I have, for example, a flashlight and a mirror, I point it, I see the flashlight, the light coming back, and it takes the speed of light, very short amount of time to come back to me, and everything is fine, but I see the same thing if I'm at rest. But what happens if I'm in the train and I move at speed which is even close to or some order of magnitude as speed of light? So it does up and down for me. I see very nice up and down movement. But what you see is not up and down movement. You see this kind of movement, right? It kind of goes like this, goes like that. If everything would be constant to everyone, the light takes the same time as it takes for me, to units. But for Pare, or you, it moves longer distance than it moves for me. And this causes the whole kind of conflict. How do we sort this out? And this is what special relativity is.
Yeah, the conflict is because we standing when looking at the moving train, we see that the light takes a longer time, but because the speed is constant, the speed, light moves in a longer distance, but because the speed of light is constant, it also takes a longer time for the light to hit the mirror and come back than in the train at rest.
Yes. So something has to change, and it's not the speed of light. The speed of light doesn't go any faster for you as an observer than it went for me. Okay.
Right.
Yeah. Let's go to the next one. So, what actually?
Can I ask a question?
Yes.
In this, what you showed us, you were moving, not the train.
If I'm moving here with the train.
Yeah.
Yes, I'm moving with the train.
Yeah.
Ding, ding, ding.
We still see this.
No, in the train, it is this one.
Yeah.
In the train, it is this short time. He says that it takes 1 second to come here. It's a very large train. It takes 1 second for the line to go here and 1 second to go here.
From his frame of reference.
From his
Yes.
in the train, he starts the clock when the light goes, and then it takes 1, takes 2. Then the light comes back, takes 2 seconds.
So,
But
from
when I
our frame of reference,
Yeah, but
outside the train,
yeah.
it's different.
yeah, but when I look outside the train, I see that because he's now moving at like half the speed of light or something. So it takes like 1.5 seconds to up and 1.5 seconds back or something.
so I see up and down movement. Purely up and down movement. I do see you moving as well, but I see for the light up and down movement. And you see kind of triangular movement.
So is it the same photon is moving at 2 speeds, depending on the frame of reference?
No.
And
Light,
then
the
it's
speed of light is
Yeah.
constant.
The different time I meant. Different time.
Yeah. It takes a different time for the point of Sauli says that it takes a different times than what I say. And
So everyone sees the same speed of light.
Yeah.
And that is the whole thing why this started. By the way, excellent question. This is important because everything again is leaning on understanding this. So please ask these questions which make you understand things.
So basically, the train is moving that way and you're moving that way. He would see the light as going like this.
If I would be
If you are moving the same speed as the train in the opposite directions inside the train, then the light would go like this.
Yes.
to him.
Yes.
Okay.
It is. Yeah.
Sorry, I started moving them around my
Yeah.
head.
But yes, if I run at the same speed as the train, then we are in the same frame of reference. Everything is except the train, but we don't care.
But if our trains moving against each other, then we see like even more exaggerated. So the photon in the other train goes like even in a shallower angle or something.
Yeah.
And don't be surprised if it takes some time to understand this because we go like through a basic half-year university course or more during this course. So in 1.5 hours, it's impossible to teach this stuff.
And for that reason, we left all the equations out. I hope you are.
I have a short comment. Maybe the hydrogen Moore experiment is the important part here because basically that sort of was the failed experiment which tried to have this brain situation and have the option that the light speed could be different and could vary.
Yeah.
But the experiment failed and it stated, or the result, the only obvious result was that light speed has to be constant.
Yeah.
So the other parameters which you have, you have time and length,
Yeah, we'll
and
go
they
into
have
that.
to vary.
Yeah, we'll go into that. And it failed to prove what they were set out to prove,
Yeah.
being very, very important and successful experiment.
Yes.
Okay. So I'm moving with relation to Pare and you, then you see that my length on the direction of movement will be shorter. So I will be thinner. My mass will increase. My clock will run slower. And the last one, of course, events that you think happen at the same time but at different locations, that's important, they do not necessarily happen at the same time for me. And all of these have very nice formulas, which we don't go, but I'll show you just this Lorentz factor, which is, this is here speed, so about here it is light speed, and here it's 0, and this is the how much you have to correct these lengths, masses, times. So it is very close to 1 until somewhere here. It doesn't really matter unless you have precision instruments. But when you go towards light speed, this basically shoots through the roof and you never reach the light speed. Whatever you do, you never, from any other observer, reach the light speed. Your mass starts to go to infinity, your length, your time, all of this gets skewed very badly. So when we talk about relativistic speeds, we basically talk about these where you see significantly, for your purpose, greater than 1 Lorentz factor. Our examples most use 0.5 because you already get some amount of things there. Okay, let's go to next. Now, this is the next phase where I want you to pay attention because we use these graphs and I want to explain you what this graph means. So here is where, for example, the rocket is moving this direction. So this is our physical, if this would be train, this would be the train track. It only goes one way. We don't care if it raises up or goes sideways. And this is time. So we have a guy standing here and rocket. So 5 time units, let's say 5 seconds. The guy who is standing is in this place, but the rocket has traveled some amount. If this guy has a flashlight, turns it on, at the same time, in 5 seconds, it's this thing.
Also because the second axis, we can go some into this because this is kind of important. Because these time units are in seconds. Let's say they are in seconds. But then in relativity, the distance is also measured in seconds, which kind of can confuse things. It did confuse me for a long time. So kind of 10 here is the amount of distance that the light travels in 10 seconds. So it's basically 10 light seconds. So in this case, it's kind of, if this would be Earth, Moon would be somewhere around here. So these distances are very large in basically anything.
Moon is about 1 light second. So Moon would be somewhere here.
Well, somewhere here.
Yeah. Moon would be somewhere here. So in 1 second, the light would hit the Moon. This is half light speed. So in 2 seconds, this would pass Moon.
And these lines are in 45-degree angle. These are the light speed. This is the maximum speed you can get.
Yeah.
In all these diagrams, we draw the light cone here, basically.
That is the meaning of the light. Now I understand.
Yeah. So, and when we talk about causality and simultaneity, anything that is beyond here is kind of out of bounds. This guy cannot impact anything that is here in space-time. Now we have the time and kind of one space input. The one reason for this is the causality, this kind of what can happen. The other thing is that when we change the frame of reference between the guy and the rocket, these stay the same. They don't move in any of these things. even though we apply the same formulas or whatever, the light is moving at constant speed, so they don't change. Everything else here will change. So,
and also the time here and distance here are relative to this guy who stays at rest. These are all so that in this case, this is how this is the time that the observer here, what the stationary observer sees from the looking at the spaceship. So he can see that at the time 30, it is at the time 30 it is at 15, I think. Yeah, 15 units away. So half light speed.
So, what happens when we move to this frame of reference, to the rocket's frame of reference? We do this kind of in steps that we do a twist, so that you see how it moves. Can you move to the same? So, now we have partially moved the frame of reference to something that would move compared to this. And then, if you go and go. Now, from the rocket's frame of reference, it's at rest. It's not moving anywhere, but the guy who was looking at it is moving away. Rocket moving that way, so from the watcher's point of view, but if we look at the rocket, then the guy who was looking is moving away. You note that what happens here, this rocket thinks that 26.5 seconds has elapsed, and the guy is kind of in totally different time. Not totally different, but different time. Does this make any sense?
Was the first slide, was it at 30? No, first. Don't spoil.
Sorry.
So it was at 30.
30 seconds, yes.
Okay.
So this, when we just changing the frame of reference, came somewhere here.
You see, yeah, because this is kind of the clock. That this guy has a clock, and he looks at the clock and now sees that this is at that point in time. His clock says 30 seconds.
Yeah, don't move yet.
Yeah.
Okay, now again simultaneity. This guy thinks the rocket is here at 15 at
30 seconds.
15 light seconds at 30 seconds. If you go to now at these are not at the same time. Every same timeline is here. So this guy sees something else. I think at this being at 35 seconds, somewhere totally different. Okay, I don't have the numbers, but anyway, everything changes, not just the time, but the distances. And
And you have to remember that this is the same. These are the same events, so this is kind of the same guy in same point in the space-time continuum. So we are just looking at one part of that, and this is kind of the same event or same situation that this guy said that this is at 30 seconds, but this rocket's clock has only gone by 10 to 6 0.5 seconds or something.
When, if I understand it correctly, the watchers in the rocket sees the guy way later on their clock.
Because this guy says that this guy is going farther away, and if this rocket would go in 30 seconds and then look at where this guy is at the same time, if you look at this, because the rocket flies as long as so long that its clock says 30 seconds. So it's and then it says, where is this guy? Well, this guy is only here because this is kind of where this guy is at 30 seconds. So which comes when we come back. When we come back here, it says that this guy is all here when the rocket is here. When the rocket is at 30. No, when the rocket says it's 30 seconds, this guy has, from the rocket's point of view, the rocket sees that it's only here. So it's kind of.
So basically, the problem is, or the thing is that distance and time both vary same time.
Yes.
You cannot just pick the other one.
And mass and speed.
Yeah, but they are the same.
For this.
Let's start with the time
Yeah.
and time and distance.
Yeah. Okay, let's go to the next example. So, now we have a situation that someone is looking here at the rocket, and the rocket fires a laser. As noted so many times, light moves always at the same speed, so these move at the same speed. This original light beam here, and this what the guy shoots. So if we change to the rocket's frame of reference, you see that everything moved, these guys moved as previous, no change here, but also no change in here. The light is still moving at the same speed. For each one of these perspectives, the light is always moving at light speed. Okay, let's go to next one. Then, one before, is this wrong? No, okay, yeah. Yeah, so, now the units are much smaller, like nanoseconds or something, and I am flying in a rocket with a mirror. What I see is my face, photons going to the mirror, bouncing back. Happily, I see that. I see it hitting the mirror at halfway and then hitting back my face, or eyes in this case, at equal distance. So, mirror stays while I'm traveling at constant distance from me. But then if we look at, from, for example, Pare's perspective, what they see is the light takes a long time, again moving at speed of light to hit the mirror, and then much shorter time because the rocket is coming back, or I'm coming towards my mirror, flying towards my mirror, or the place where it bounced. So again, simultaneity is different for different perspectives. Does it make sense? Okay, I think we have at least one more example.
Yeah.
So Einstein here, two planes are coming, head of plane, tail end of plane. They meet here at certain point, very nicely overlapping from my perspective each other.
Yeah, they're flying towards each other at the same speed from our point of reference. So we're kind of standing still, and there is one plane coming at some speed and another plane coming from the other direction at the same speed, but opposite direction.
Yes. So if we zoom in, so first we do two things. We zoom into this place and we look at from the red plane's perspective.
And you can first you can see that from our point of reference, the planes meet at this point in time. They are at the same. They kind of pass each other, so that we can see that they are at the same. There are two planes which are kind of
Head and tail.
Head and tail coincide at the same time.
But from red plane's perspective, what happens is, first of all, the other one, which is moving fast, is much shorter. It actually should be thicker, but this is for purposes. But the tail end, and when the red plane's head hits the tail of the blue plane, these do not anymore happen at the same time. Again, simultaneity is not something that survives near light speeds. Okay.
Yeah, and this is kind of the effect that why things seem shorter, because from the, of course from the blue plane's point of view, it's the same when it's the red plane's tail hits the blue plane's end, then it then the red plane is much shorter. So this is kind of the blue plane would be kind of in its frame of reference. It would be like going in this direction, because it's kind of it's different. So they don't see that the head and the end of the plane are not simultaneous in their other frame of reference. And this is difficult. So
Please ask questions if yeah, go ahead.
So, in the blue plane's world, the red plane is bigger and it's sort of
Yes.
and all the laws
No.
of physics
In blue plane's world,
other is smaller.
you just flip this picture and change the colors.
Yeah, but this is the red plane's world.
This is
So,
red plane's
so
world.
in the red plane's world, the blue plane is smaller, and
Yes.
all the laws of physics behave as
Yes.
if the blue plane was smaller.
Yes.
But in the person's view, the planes are the same size, and
Yes.
yeah.
And sorry.
Here at the stationary, our perspective basically is that the planes are shorter than they would be at rest, but they are the same size. But from the planes themselves, they look different.
Yeah. And from blue plane's frame of reference, red is shorter.
Yes.
So the exact opposite. Which gets us to twins paradox. So, as I said, we showed the first picture. When we changed the point of view, the other clock was running slower, right? You remember that? But all frames of reference are equal. So, if we switch them around, if my clock is slower because I'm moving and Pare is stationary, if we look from my perspective, Pare is moving and Pare's clock is running slower, which leads to situation, but what if I come back to the Pare? I move away and come back. So whose clock is running slower? Frames of reference are equal and whatnot. So what actually happens? And there happens this, why we did anchor this into moving at constant speed. My clock will be running slower because I didn't move at constant speed. I had to turn back to get to Pare. And hence, all of this still holds. Because I didn't stay put or in constant speed. And this kind of is expanded a bit in the general relativity, but otherwise you just have to believe me that this is how it happens. I have seen multiple versions of this. Some versions use the graphs which we showed, that if you do this kind of switch in, you get my clock slower, which is fine. I have seen another example as well, and so if you want to dig into deeper, there is material on this, but that's for you now. Treat it as like this. That's my recommendation. Okay, let's go. Yeah, we touched this subject already. So, speed of light, c, is the constant. Nothing goes faster than it. It is 300,000 kilometers per second, or 300 million meters per second. Quite fast, travels around world 10 times or 8 times per second. 7 times. It's over 7. Yeah. And because what we showed, okay, well, let's go to the FTL later.
Yeah, the causal, we come to the causality thing later.
Yes. Okay. Let's go forward. Okay. You still have to hear my voice for a while before Pare takes over. So when Einstein was making this general special relativity, he came up with this formula energy is mass times speed of light squared, which basically means that mass and energy are two forms of the same thing. You can convert energy into mass and mass into energy. And because c squared is quite huge, this means that when you convert mass into energy, you get a lot of energy. A lot. This also means that if you have, let's say, coal molecule, you burn it. You release the energy in the coal.
Or in the covalent bonds of the coal, so this is kind of chemistry, but
Yeah, this is kind of chemistry. So you get energy. And if you measure the weight, the end results, you get less mass because some of it was transferred as an energy. You get actually very little, so it has no practical use unless you are using very, very specialized instruments. You get per kilo you get 33 megajoules.
but then of course you can, of course it's relatively what's used, because of course you can, if you have 1 kilogram of coal and you can like barbecue a lot of stuff with it, so it doesn't. But you can produce much electricity with it. So
Yes.
so.
But when we start looking into nuclear power, nuclear weapons or nuclear power, it is 7 orders of magnitude bigger what you get per kilo, just splitting plutonium into whatever it was, radium or So, And again, if you manage to have some antimatter at hand, hopefully not, because it destroys your hand with annihilation, you get again 3 orders of magnitude bigger amount of energy. In coal, almost nothing is lost on the energy. In the mass. Here in fission, it's about 1,000th. What is lost?
In fission it means that you have a nucleus of plutonium, and then it splits into other nuclei or other elements, and these weigh a bit less than the plutonium nucleus, and this is what's converted into energy. So it weighs a bit less than the product weighs a bit less than what was.
Yes.
In that antimatter, of course, everything is converted. So if you have 1 kilogram of matter and 1 kilogram of antimatter, and you annihilate them, you have nothing left except energy. So this is kind of the all you can get out of matter.
Okay, but this hopefully is clear. Energy, matter, same thing, different forms. Mass is more of an inertia, so gravity impacts it a different way and so forth. Okay, let's go to general relativity. And now, Pare, it's your stage for a while.
Yeah, because like you remember, everything we have talked about this far has been these frames of reference moving at constant speed. And this was what Einstein did in 1905. This is what he first published. But then he began to realize that, he realized it before, but especially on on Earth, gravity. We have gravity, so everything is basically accelerated all the time. And in this case, he also realized that the gravity is basically the same as accelerated motion in this frame of reference. So like we have rockets. So if you are sitting in a rocket, well, this is kind of gravity is equivalent. So if you're in a rocket and this is closed, so basically somebody standing here can't tell if this is moving or in a gravitational field. Of course, now in a gravitational field, so somebody sitting or standing here would feel that there is a gravitation or gravity somewhere. But if this rocket would be in space and moving upwards, accelerated, then the same person couldn't tell the difference without looking outside. Is the rocket moving or not? So there is no way of doing that. Of course, on the planets, the point is that the gravity is not down. Is down to the center of the planet, but it's kind of different for other places because Earth is a round planet. So basically, you get also these curved frames of reference. And special relativity works, well, space and time are treated the same. I can't remember.
You also get differences between how close you are to the center.
Yes, of course. There is also how far you are. So the gravitation
translated instructions for scales that are so precise that if you move from one floor to another, you need to re-par the scale.
Yeah. So this basically means that we think that there is a three physical dimensions, and then time is something different. But basically, what Einstein used as a basis for the general relativity is that they are not separate.
Yeah.
They are one thing, and when you start measuring things in that, you have to look at all four.
Yeah, but the thing is that if you measure something physical in one frame of reference, it's kind of this 4 value which has this spatial dimensions and time. But when you move it to the other, it's the same thing, but it's like all the numbers change, but it's still kind of the length of it is the same basically. In most of you can have this with different variables, but anyway. And also the special relativity works when there is no gravity and acceleration. So it works in small areas, even if you have acceleration, in small areas and short times, you can still use special relativity. Like in this room, like we know that there is no, because the gravitation in this room doesn't change much, so you don't have to take into account that. And when you add the gravitation to the special relativity, we get general relativity, and this has lots of effects and kind of unexpected effects, which we will see next. So the first is that how do we get this gravitation thing, and what it is? So it's kind of property of mass. It used to be thought as property of the mass of the objects, but general relativity says that no, it's not property of the object. The object just basically bend the space-time. So the space-time is kind of this continuum where things go straight, and these objects bend it so that the straight line is not straight anymore from the outside perspective. From the object's point of view, it's always straight in general relativity. And we see this as general or this bending as gravitation. So basically, Earth bends the space-time around itself so that everything we stay here and everything stays here on the surface of Earth. And the objects which move also bend the space-time themselves. So it's kind of the calculations are not well for easy cases they are easy, but mostly general relativity is not very easy to calculate. And also, like we looked at when in the special relativity, that speed causes time dilation, but gravity also causes time dilation. And this was kind of first thought looked at in thought experiments, like when you bounce a photon upwards into the ceiling, the photon here has more energy than the one up in the gravitational field, because it kind of it loses energy in there, and then the time dilation is, and then the time is moving slower there also, and this is not very easy thing yet. But usually the time dilation is very small, because which is why it was noticed in a bit over 100 years ago, or realized. But the massive body has this, like a black hole has time effects. Like if you were close to a black hole and try to light a flashlight out of it, you would see time dilation, and time dilation things happens near black holes. Not so much here, but there is still, like, the GPS has also so precise instruments, so they are like I think 10,000 kilometers, something like that, thousands of kilometers above the surface of the Earth. And they are so much above above us in the gravitational field, so we have to correct that. But also for the speed, so it's going backwards. So the speed says that time is moving slower or faster, and then.
The smaller gravity means we are
moving slower.
So yeah.
So, and this general relativity is difficult stuff, and we don't claim to understand this very well because we haven't really studied this.
Special relativity is very easy formulas. It's square roots and things into second power. Whereas this is tensor mechanics, basically. Stuff that I didn't, for example, in my studies in master's degree, didn't more than touch. So
Yeah.
I couldn't make these calculations.
I also like did some tensor calculations and not in special or general relativity. So I can't even calculate these properly. Probably we could if we took some time and energy to time and mass and energy. Okay, but then we come to the what happens or what can we do with these things? Like black holes are kind of one thing that comes out of the general relativity. Of course, they were predicted much before, like almost 150 years before the theory of relativity. But this was like Mitchell thought of can there be such big planet or such a big star that the light can't come out of it. So that's kind of nobody did any calculations, but they just thought that okay, this might be possible. But then with the general relativity, they first thought that they had some solutions to the equations that we can have objects so massive that the light can escape them. And there are theoretically many types of black holes, and we haven't seen one up close yet. And we know that they exist. We have proof of that, and we have had that for a long time. So we know that there are black holes, but theoretically they are not easy objects. So the theories have multiple different black holes. Like the usual first one we do is this Kerr black hole, which is kind of non-rotating. So you just have a lot of mass in place, and there's a ball of singularity, or a ball of event horizon around it. And then when you fall into the black hole, if you go, the thing to remember about black holes is that they have an event horizon, and when you go inside that, you're kind of doomed because you can't get out of it anymore. There is no surface; it's just the gravitation is so big there.
And if you would be inside and you have flashlight and you show it out, the light will curve back to you. It doesn't go anywhere.
Yeah, in reality, most things rotate in the universe. So the real black holes rotate too, and we can see them, or some of them, because they have this accretion disk. So because they are usually close to a star, and they rotate and they pull the star, and then all that matter goes into this disk around it. But there might be some black holes we do not see, so because they are black. So if you point a telescope at them, we don't see anything. There are gravitational effects where we can see those, so they act as a lens, so we can see them. And so the event horizon is the border in which light does not return. So of course, it's very hard to get near a black hole close enough to shine a light from there. But the features of the black holes, well, they are mostly featureless because they have only three different things which matter. They have mass, rotation, and electric charge. And the electric charge is basically zero for anything large enough to be a black hole, mostly. So they have mass and rotation, and you can't really tell from looking at the black hole what it was before it became a black hole, because they all look the same. And because mostly the black holes, usually the real black holes have an ergosphere, so it's kind of like rotating. They have this event horizon where you can't come out because it's so massive. But these have this ergosphere, which is possible to. You can't stay still there. You have to keep moving, or otherwise you do that. And if you go near, because there are lots of sizes of black holes. There are like stellar black holes, which are made from an exploding star, and they are kind of these close by black holes. We have some evidence of those. And they are so small that you really can't get to the event horizon because there are these tidal forces, because the gravity is so large and the change in gravity is so big if you would stand or veer near one with the feet pointing at the black hole, the gravity at your feet would be so much bigger than the gravity at your head, so it would kind of stretch you into a line and then you would die. So, of course, the gravitation itself is usually massive. So, if you would stand somewhere, you would probably.
Now I'm just looking at the clock. How many slides we have left? Okay.
12.
Yeah.
No.
Oh no, we're in good time.
Very good. But then in the center of galaxies, you can have large black holes, which are so large that you could go to the event horizon and not die because of the tidal forces.
You die because of the gravity's strength, which is.
Yeah, but if you're a rocket around then you can survive. Yes. But depends. And black holes, kind of, this is quantum mechanic effect, and nobody has really seen it. So they basically evaporate, but they evaporate more the smaller they are. And I think every black hole we have evidence of is so large that the evaporation, the cosmic background radiation gives them more energy than they evaporate, so they won't evaporate yet. But this year we also got this first image of a black hole. So this is kind of the Messier 87 black hole. So this is very, very large in the center of the galaxy, which is like 7 billion times the mass of the Sun.
Can I mention something?
Yes.
So, this is a picture of black hole where you don't see the black hole. So, it's black. But as Pare mentioned, usually anything this size has some material coming close to it, and because of the gravity, it speeds up and starts the accretion disk, it's called, to glow. And that's what we see. And this matches the predictions we had, or humanity had, for how it would look like. And they can do quite a lot of stuff from that.
Yeah. So basically the black hole is the black area here, and this is the accretion disk. And because we don't see it kind of head on, we don't see it head on from like there's a hole and then a disk around it, but the disk is somewhat rounded. That's why it's brighter on the other side, because the gravitation of the black hole kind of moves the photon, so we kind of see also the back of the black hole partly. So this is we could have a presentation about this image. so this is a very interesting image. But
Yes.
we know that there are black holes, and they are kind of one of the proofs of general relativity. So but nobody still knows what goes inside of a black hole really, because even that our physics break down at the center of the singularity of the black hole. You know, we can say something about what happens inside the event horizon, but we don't know really how they work. You can probably get a job doing that if you want. If you go to get a PhD in that.
Okay, let's go forward.
So now we go into this kind of. This has all been this far. Everything has been real. So what exists, what we know, really exists, and what is. In acid black holes and the stuff, there are like neutron stars and that kind of stuff, which also can use general relativity. And there is of course like cosmology, which you can do, which we don't talk about here. You can also study that, and there is a group in the Helsinki University doing cosmology. I think multiple groups. So if you're interested, go and study there and work there. But now we get into this how to get in, partly what can you use in a role-playing game or setting? So we get the wormholes, which of course have been a staple of different space settings for a long time. And general relativity allows wormholes, so this is not something that that's completely we just invented, but kind of it allows, but nobody knows how to do them. So wormholes basically connect 2 points in space-time so that there is like a shorter distance between them, and they are kind of easy to fly through. If you're large enough, it's easy to fly through. Nobody knows, of course, what they look like. Something might be that there is like this black hole at the other end, and there's a so-called white hole in the other end where matter just comes out of it. But nobody has ever seen anything like a white hole, so there is no evidence for this. But these are also possible time machines, which is kind of fun. So you can have a wormhole somewhere, and you move the other faster than the other. So the time flows differently in the other end. Like we saw in the special relativity discussion, that if you move something, the time moves differently. So if you have portion of space which you move different at a faster speed than relative to another, the time flows differently, and you can use it as a wormhole. But this doesn't really, nobody knows how to do these things, because even though general relativity allows wormholes, there's exotic matter needed, which has negative energy density and negative pressure, which is kind of things we don't know how these would work. Looks good, huh?
No.
So this kind of like, yeah, you can have those in your space-time. Like there are some solutions where there's a wormhole, but it closes so fast that nothing can get out of it. So here's a picture of a wormhole. So basically, you can go inside there and then go. Like if this would be a black hole, or this would be like in this kind of discussion, this would be out, and then this would just continue forever. Or a planet, it would be like a ball continuing with that. But that's kind of a easy way of seeing that there's space there, and then you can go through the wormhole. But it's very curved, so basically, if the curvature is gravity, you can see even in this picture, if you would have a wormhole like this, there will be quite a lot of gravity because this is so curved. So things would be interesting in the wormhole.
Okay, then some practical things about traveling near the speed of light. The math is there, but also internet you can find million calculators about this kind of stuff. So if you want a world in your role-playing game where you travel near speed of light, use one of these calculators to get the kind of time dilation. Here is a table with some examples. If we travel at half the speed of light, going to Alpha Centauri, that's 4.37 light years away. It takes, if I go there, Pare sees me traveling for 8.74 years. I see a bit shorter amount of time, so I get there as kind of a bit younger. But also I see the distance shortening. My distance to the planet is getting shorter. And as we go towards the light speed, these start to get quite require a lot of energy because of the mass and mass dilation, and such. We start seeing things like if we could get to 0.999 speed of light. Again, Pare sees me almost traveling to light speed. I saw just a couple of months spent on the ship traveling not very far. I would be much younger than Pare at that point. Of course, frames of reference, I wouldn't notice it until I would get back to Pare, and then that would be kind of clear. But this is just to give you an indication what happens. You travel fast, you get there faster, the distances seem shorter, but someone looking from outside sees you still going less than speed of light. Just to give you an indication what it would mean in real physics, not any fantasy world physics. If we have a rocket which is accelerating at 1g, it takes a year to get somewhere here.
Yeah, and we don't really have any engines at the current time. We don't have any engines which would go really at 1g for a year.
For a year.
It like lots of reaction mass. So whatever is accelerated near light speeds would be very small. So you kind of need fantasy engines for this, and so on.
But anyway, I think the most important thing is if you want to use these, use some of the calculators around web for these. Shall we go? Yeah, of course.
Just to be clear, because I wasn't sure if I understood the there and back again idea. So if you would go to Alpha Centauri with the 0.99 speed of light,
yeah,
you'd age about a few months, and
yes,
Violet would age for 4.5 years almost,
yes,
4.37. And then let's say you forgot your wallet, so you fly instantly back.
yeah,
You would still only age about
yes,
0.4 months during this whole
yes,
this whole
yeah,
travel over 4 years.
Yeah.
And you would be about like 9 years old.
Yeah. Because when he travels to there, he has to first accelerate to the light speed and then decelerate back to zero speed,
yeah,
basically,
and
and
then
then accelerate again.
yeah.
So that's what creates this difference.
Yes.
Okay, yeah.
So that's the twin paradox thing. Yes, and you understood it. Correct.
Okay, just checking, because I wasn't sure if you said that it cancels each other out.
No,
I just misheard.
If it would move at constant speed, which it cannot because it has to
Exactly,
accelerate.
yeah.
So the acceleration breaks the twin paradox.
Okay.
So that's the point, I think. That makes the aging thing.
I mean, one of them would keep accelerating at a constant speed indefinitely, then they would stay the same age, but they would never meet again.
Yes.
Okay.
Yeah, no. But there's of course these things you don't have to. This is of course if you look at from the point of role playing this, so kind of even if you had like this world where you can do like 0.999 to different places. So everybody on the ship would age like it's a couple of months later. There it is. Then you're at the next planet, well close in a close by star system. But then you would have to have like the time at the planets in the star system would go like over 4 years forward. So you could have interesting campaigns, but I don't know any campaign worlds which would do this. Mostly have that light speed things.
Yeah, and in this my example, 1g of accelerator, 1 gravity of acceleration. From Parviaisen's point of view, you wouldn't actually get this far. You would get, I don't know, maybe 0.75. So it actually, from the observer's point of view, it requires a lot of energy to get here.
Yeah, and of course you have to, if you're doing realistic campaigns, you have to realize that there's still some matter in between stars, so it's not empty. So like gas and hydrogen atoms or something. And if you bump into something at that 0.999 C, it's like coming at you at that 0.999 C, and the collision energies are very, very high. So it's kind of you need to, if you want to go realistic, you have to invent something there in front of that. And probably it's impossible.
Some kind of shield.
Yeah, some kind of shield, but then so it's anyway science fantasy if you want to do even near sea travels.
Or some kind of event horizon, like bubble.
Yeah, something. If you have a black hole in front of your ship, it's kind of a good shield, but they're kind of hard to control.
What does algorithm drive?
I don't remember. But and of course that there's like this one thing we didn't realize is that the gravity because gravitation is part of it's not in the slides, but gravitation is caused by mass basically curving the space. So if you have like something like artificial gravity in your campaign, it's kind of like you have to basically say that this creates it bends space and then it looks like gravity. It looks like a big mass basically. So it's
Yeah.
or you can have different things, but it's anyway magic technology.
My opinion, anti-gravity wormholes, do whatever you care.
Yeah.
We know so little about those, especially anti-gravity, that it goes to the realm of magic.
It is magic science.
Yeah.
Same with the FTL, by the way.
Yeah. But then there's like one thing that near Xerox, which was in traveling mail, it's like 20 years ago. This is role playing stuff. So basically, the point of this was that Traveler, some versions, Mega Traveler at least, has these constant acceleration drives, which don't require anything. They just want electricity, and they had like 6G drives, which is much more than 1G. So you could basically go near light speed with those drives. But somebody realized that if you have this drive which goes like 6Gs indefinitely with no, of course the game didn't have any rules for relativity, so nothing happens. But then you take an asteroid somewhere far, like in the Oort clouds, like light hours away, so nobody sees what you're doing. Put a 6G drive on it, point it at the planet, so it kind of needs some energy, like a lot of it. So, but if you have these travel and magic drives, when you get, if you have 6C drives, it takes like some months to go to half C, I think. So it's possible to do that. So before somebody sees it, and then you when somebody sees you, because if it's coming like 0.99 light speeds, like in our solar system, it's kind of like from the Jupiter, it would take something like 40 minutes or something to reach Earth. So you have 40 minutes warning. So what do you do with this rock which is coming at you?
Yeah.
0.9 light speeds.
But what happens there is, because you see the light coming, the light only comes marginally faster than the rock, which means that you actually don't have 40 minutes.
Yeah, you don't have 40 minutes because you have much less.
You see it at Jupiter and you know it's 4 minutes away or something like that, and there is not much you can do.
Yeah, and of course there would be like this, it would need immense amounts of power, like this fractional and constant acceleration drives. But it would also be like this these would be like to destroy the whole planet, kind of.
How about planet?
Unfortunately, ending it would be also really damn hard.
Yeah, but the planets don't dodge much. So,
If you
kind
manage to aim it right, then no problem.
yeah. And you don't need a big rock like this kind of like small asteroid would do fine because it's going so fast. But this is one thing, and on the travel and mailing list is kind of a forbidden subject. Do not talk about this because they didn't the writers of the game didn't realize this, and nobody uses it, and it's not talked about in the game. And on the mailing list, created some heated discussions there. So,
yeah.
Let me take this.
Okay. A bit about antimatter. This antimatter is here because of the E equals mc squared, which kind of gives us a very convenient formula how to translate antimatter into energy. So antimatter is matter composed of antiparticles like positrons, antiprotons, and others. And they have this nice feature that when they come into contact with their counterparts, they annihilate, releasing all the energy, pretty much all the energy they had in the particle. And that is, as shown in the energy equivalent thing, is really, really much. So 1 kilogram of antimatter gives us boom like Tsar bomba. I don't know if you know it. It was Russian something like 50 megaton nuclear warhead, biggest one ever exploded. So 1 kilogram of antimatter gives you same amount of thermonuclear weapon which weighed at 67 tons. Antimatter is not fiction. It is thing that we can manufacture. The problem with that is that how do we store it? Because if it gets in the way of normal matter, it annihilates. So there is some ways of doing electromagnetic fields that keep it stored. But that, of course, means not only weapons, but as an energy storage. If you manage to generate antimatter and store it efficiently, not like ton of something per gram, you get quite a nice energy battery or energy source. So here, the manufacturing can be done. It's tedious. It's I don't know, atom per atom, basically. And then you need to capture and you need to store it. And yeah. On the other hand, compared to, for example, char bomba, you need quite tricky things to get actually that matter to. It has both fusion and fission to explode. Whereas here you turn the magnetic field off and. Yeah. Okay.
Yeah. I think this is the last part of this. So this is faster than this is going. Now what happens when you go faster than light? So basically, like we saw in this how to travel near sea travel or near sea rocks. So you need immense amounts of energy, and even then it's not that fast. Like might take a couple of months or a couple of years to nearby stars. So kind of not easy. So other star systems, so you can build a campaign on that, but it's kind of not. I don't think any game which does that. So you might write one which is good, but or play one that is good. But then we look at what happens with the theory of relativity. Now it is more to special relativity again. So and faster than light is basically moving time-wise. So we're moving in time. Because if you look at the diagrams, it's kind of like, if you look at these diagrams here, so basically everything that moves here is like space-like movement. This is time-like movement, which is kind of difficult to understand because if you move around here, we're moving in space, and if you move around here, we're moving in time. Which is kind of not an easy thing to realize. But then, if you have faster than light drives, it always allows you to have causality breaking, or something happens before something that caused it happened. So which basically means time travel. And there's this physics math on the internet. You can Google him, and there's, I think the link is in the link list. So there's the big two: relativity, causality, and faster than light. So now we're kind of in the real world. We of course pick relativity and causality, or as far as everybody knows, or we know. So might be there's FTL drives, but kind of would make a different world than what we have. So again with this, now we get back to these space-time diagrams. So basically here's again. Now we are at some planet here, which is stationary, and there is some other planet equidistant away. So kind of these are in the same place relatively, and it doesn't really. They don't move. And then there are of course these light rays which says that the idea this is the space. This is the light cone where you can do. And there's a spaceship going around. I think this is 1.8 C now, so it's going very fast towards the other planet. And now it starts at time 0, flying towards the other planet, and at this static frame of reference at something like 18 seconds, it reaches the other planet. But then, at the time of 10 seconds, we have this FTL phone we call. There is this. Can you do something about the spaceship that's coming around you? And we call it, and then it takes only 5 seconds for the message to go through. So this is faster than light. Even though if you would like to draw the light lines here, it would start something like here. So everything that starts from this 10 seconds on this planet and goes in this sector is faster than light. So we see And from this point of view, from the planet's point of view, the call happens here, and the message call is received here. The message is sent here, and the message is received here. And then the spaceship reaches the planet after that. But when you look at this from the point of the spaceship, things get different. So here is now the first planet. Its world line is here, so it's going backwards at point 8c. And here's the other planet, which is coming towards the rocket at that point 8c from the other direction. But now, from this spaceship's point of view, it says that, okay, at this point of time, at 5 seconds it can't receive, but at 5 seconds, in the spaceship's frame of reference, the call comes in, that yeah, there's a spaceship coming. But they're like, okay, but that spaceship's like, hey, why did the call come? Because at 5 seconds, it's still here, the timeline of the planet is here. And then the planet does something here, and then they do something. They'll tell the planet, hey, we got a call from the planet. Yeah, you got this. We got a call, but there was a spaceship coming. And then what happens if you have? I don't have a slide about this. What if and this is like the phone call has in this spaceship's frame of reference, the call hasn't been placed yet. So if the spaceship has same kind of FTL phone, they can send a message from this point, from the planet, hey, and send it back to this planet, saying, hey, you call this planet, don't call, don't tell them we are coming. And then they send it, and because it was fast, the call from the spaceship back at fast FTL comes around here, which is like, and then and what happens when they don't call? They get a call from the spaceship, don't tell us we are coming, and then they don't tell. But will they tell? Did they get this visit or not? Do you understand? Because this is kind of complicated. So, because you have to trust that these figures tell the truth in the correct way. But if you have FTL, but you have to remember that if you have FTL in some frame, in some other frame, the causality is different. So things happen before they are caused. Yeah.
So if you had this FTL phone, then from the rocket's perspective you can go back in time, but from the planet's perspective you can't.
Yeah, basically you have to move fast enough. So it's kind of this is very difficult. Might be difficult to pull off depending on what. So in this case the rocket was going 0.8c and then calling back.
So what Pari is showing here is of course a contradiction. So applying physics into this makes no sense. But he's demonstrating why it doesn't make sense. So FTL gives us problems. We are just showing how they would cause in this special case. But the whole point is that we should never get into this, at least.
Yeah.
Our current understanding of physics.
Yeah. Because this says that this thing. Well, let's say it's not a phone, but it's an FTL drive. So like a spaceship Odyssey or something. To pick some example, but it goes from the spaceship Odyssey makes a jump from here to here to avoid the machines, and then but in this frame of reference, the spaceship appears somewhere and then it disappears from the air. So basically, in this case, there would be two spaceships around here because if the spaceship is on the planet and comes here and then jumps back in time. So this fast-moving ship can basically see two spaceships there.
This would be very convenient if you're running from aliens. You do this kind of mechanics and always get a call. No, don't jump there. It's a bad idea. Okay, we don't jump there. We'll jump somewhere else.
Yeah, and of course I think this is kind of the things you can get. Of course you can get paradoxes, and I think Warhammer 40,000 has examples of time travel and jumping and so all that stuff. So which creates problems, and it does kind of fun things. But the kind of thing to remember is that if you have FTL, you also have time travel. So might write a novel about or a short story about this, but I'm not sure how to apply this in a game because in role-playing games, time travel is problems.
Or you have to have separate dimensions when you travel to the jump field. You cannot communicate.
Yeah. But if you it doesn't matter if you just disappear. It doesn't matter if you disappear from. Let's look at this. If you disappear from here and then appear here, you weren't in real space. It doesn't really matter because anyway you disappear from here and appear here, so you appear before you were disappeared. It doesn't matter. Any way of making faster than light gives you
actually, if you have another light cone, you cannot send message back before you move.
But if you have
time reference,
it depends.
Yeah, but okay, but that's kind of a thing again where you find completely magical solution to a problem which we shouldn't have, and if you do that, that's fine. That's what I like playing role-playing games. That you can generate your own worlds where you can do things. We are just demonstrating that you need to do your own thing.
The problem is it constantly breaks.
Yeah, and that's kind of difficult in a little bit because you have in role-playing games you mostly have linear time. At least when playing them. But those were our slides, so thank you. And we have 15 minutes, so if you have any questions or comments or.
Okay, I have one question and a small thing.
Yes.
Okay, if you can use a little amount of mass to make a huge amount of energy, how does it work to use a huge amount of energy to create something, a little bit of mass?
It works. If you have, let's take a very simple example. If you have O2 atom, oxygen atom, it's O2. Molecule. If you separate those two, you have two oxygen atoms. They have more mass than the O2 did have.
Yes.
So that works. If you want to kind of construct energy from nothing, that works also, but that gets very tricky. There are some examples, but that example is quite bad, but it is possible.
Okay.
But of course, if you look at the antimatter, how much energy you get from annihilating them. So even if you would create 1 gram of matter, you would need a huge amount of energy. So it would be kind of difficult to arrange.
Yes.
So
if I'm interested in like creating worlds, I would need like a.
Oh yeah.
yes. You're better off just collecting things around.
Then you have the problem of entropy, that nothing is 100%. There is also something waste in every process.
Yeah, but thermodynamics is probably another question.
Yeah, and entropy is not the easiest.
Efficiency isn't 100%, which means when you create lots of energy and move it back, there is something which you did not convert back, which is your problem. Because, or you have to add energy outside.
Yeah. Of course, if you would like have a matter generator from energy, but with some this one. Yeah. So if you had something that would reverse the antimatter, so you would create matter from energy. If you have some kind of inefficiencies, which you always have because of thermodynamics, then even if you like have 0.001% of inefficiencies, you're heating the things up by pretty much much more than the plutonium. So you're kind of heating everything up if you have any inefficiency. So you would have to be very, very efficient.
I want to go back to this producing matter. There is a thing which I don't know if you know better, these virtual particles, but basically when we look at vacuum of space, it's not actually so empty. There are particles popping up, and that's kind of the reverse of this annihilation, that you suddenly get a particle and antiparticle pair, and usually they have a different charges, so they come back and annihilate each other, but that happens. It's just then how to make that on large scale, that is
That's kind of goes into quantum mechanics.
Yeah.
And which is again another lesson. Somebody else might do that next year.
yeah. I was asked to do quantum mechanics. I don't understand them well enough. I'm not going to go there. And if this is weird, the quantum mechanism is as weird.
Yeah. This even special relativity is something you can understand well in like short course in university. Yeah, my question.
And I think you'd enjoy trying to throw a quantum entanglement communication thing into a graph with the ships over there.
Yeah.
But again, no one has actually passed information with quantum entanglement. It is quite often mistakenly reported that something is teleported or something, like this Chinese did the quantum entanglement between ground and 500 kilometer orbit thing, and it was reported as teleportation, whereas it was not. But again, I don't want to go there. I haven't prepared, and I took one or two courses of that in university. And one thing, it was 20 years ago I did that. Quantum mechanism is actually moving with the speed still. This starts to stabilize now. We start actually measuring these gravitational waves, picture of black hole and that kind of things. But a lot of the things, when Einstein figured this out, there was no way to see if it was true. It has been still, we are finding that, okay, this matches what Einstein said.
We have some tools to actually measure that.
Yeah.
And I think black holes were, like the black holes as concept were like something in the 60s or something like that. So it's kind of not immediate discovery that we have the relativity, okay, let's have a black hole, because it wasn't easy.
Also, there was this experiment that I think it was Swiss Italians that reported that they had a particle that was going speeds above light, and it turned out to be a failed experiment. That was like 1 or 2 years ago.
Yeah.
Reported very loudly that now they have break the speed of light, but it wasn't reported that they had a clock synchronization problem. So it's sort of like quite well tested, and it's going to be tested.
If you want to continue on this subject on popularized science, there's a very nice YouTube series by Minute Physics on Theory of Relativity. That was one of those videos, was the one which kind of clicked for me. They did a mechanical thing where they could do the same things we did with graphs. If we can go to.
Do you want to do this?
Okay, this I just showed that in the first example we had the rocket here, and then we switched the reference point. It was here, and that was kind of switching the reference frame of reference by half a c. If we would switch it by less, it would be somewhere here. If we switch it more, it would go there. Of course, this line would go closer to this as well. And if we switch close to this 1c, then the end point here starts to be somewhere far off near the lights thing. But when we do this kind of, it's not just that we change the angle, but it's changing the whole thing. And this curve is just to give you indication how things move when we start moving. But can you go to the link page?
Link page,
Wolfram Alpha has quite a lot of these things where you can calculate various time dilations and such things, properties of black holes. I think this was also gravitational forces, tidal forces, was that? Yeah. So if you have a huge gravity field, your head is in different gravity than your feet, and you get stretched. Link on the FTL, why it implies.
Time travel.
Yeah. Then one more time dilation calculator. I can't remember what the last one was that the
No, that's the image for the black hole because they license said that please give a link to this image.
okay, yeah. Veritasium, by the way, has a very nice explanation of how the picture forms. Not how they took the picture, but why it looks like black in the middle and brighter on the edges, on certain edges. It's very nice video. Again, YouTube. Any other questions? No. If not, thank you.
Thank you.